Hello friends, in this video lecture we are going to discuss the point by point solution of swing equation. So let us begin. So friends, in this lecture we are going to concentrate on this topic. We are going to obtain the solution of a swing equation using a point by point method. Okay, now the very first question that arises that why do we need the solution of swing equation? What is the need of swing equation or solving the swing equation? Okay, we'll get back to this point that why do we need the solution of the swing equation. Okay, so before this, the swing equation what we have obtained in our previous discussions was it was m into d square delta by dt square is equal to the accelerating power, which is nothing but mechanical power minus electrical power. Okay, furthermore we can write it as pm minus pe. Okay, in place of this pe I can write p max sine delta. Okay, so you see here this m into d square delta by dt square is equal to pa. Okay, here this m is basically it is the moment of inertia. Okay, and it can be calculated as gh upon pi f. Okay, or in terms of per unit this m can be calculated as gh upon, simply it will be h divided by pi f in terms of per unit. Okay, now you see the swing equation whatever we are having, basically it is a, see, this swing equation as it contains this trigonometric term, so it will become a non-linear equation. Okay, so this swing equation basically it is a non-linear. Okay, and as it is containing a different derivative term, so it is a differential equation, non-linear differential, and it is a second order equation. Okay, so it is very difficult to solve or to have the solution for this equation as it is a non-linear and second order differential equation, but still we have to find out the solution for this swing equation. Now let us get back to the same question which I have raised in the beginning, that why do I need the solution of swing equation? See, I need the solution of swing equation, see, because here the unknown here will be nothing but the variation of the rotor angle. Okay, so I want to know, in order to know the rotor angle variation. Okay, rotor angle variation with respect to time. Okay, so that is what we are expected to find. I'm interested to know this value. Okay, what is the rotor angle with respect to time? At what time what is going to be the value of the rotor angle? See, why I'm interested to know this. Earlier during transient stability analysis we discussed that equal area criteria. Okay, so with the help of the equal area criteria we can obtain this value, that is the rotor angle or the critical value of the rotor angle till which our system is critically stable. Okay, if the rotor angle exceeds this value, in that case the system will lose the stability. Okay, so it is easy to obtain this critical value of the rotor angle from the equal area criteria, but I'm interested to know this value. It will be the critical clearing time. Okay, see, whenever this value of the rotor angle will attain, at what time it is going to attain this value after the system is being subjected to the disturbances, then that timing is nothing but critical time. Okay, now the question arises, why do we need this critical time? See, in the power system we are installing circuit breakers. Okay, so what we expect our circuit breaker to operate before the system loses the synchronism or before the system got damaged from the disturbances. Okay, so in order to prevent that, we need our circuit breaker to operate within some specified time. Okay, so that time is nothing but the critical clearing time. Why it is so? Because you see, your rotor will attain this critical angle at this time. Okay, so if suppose if we clear that fault, if we clear that disturbance before the rotor is going to attain this value, it means that if we clear the disturbance before this time, then we can provide the security to our power system. Okay, so in order to provide the better stability, we need to provide the time setting to the circuit breakers, and that time setting we can obtain with the help of this critical time. Okay, so in order to get this value, that is the critical clearing time, we have to solve this swing equation. Okay, because this lecture, whatever we have discussed, from that we can get this value only. Okay, but in order to get this, we need to have the solution of swing equation. Now there are various methods are available for solving the swing equation. The various methods are, let me note here, the first method available is a Runge-Kutta method. Okay, and the second one is point by point method, or sometimes it is also called as a step by step method. This method is a conventional method, the step by step method. Okay, and here we are going to discuss this step by step method for solving the swing equation. Okay, so let us discuss this step by step method of solving the swing equation. Okay, see here in this method, what we are going to do is we are going to consider a discretized model, okay, of the three parameters. Okay, the first thing is, so here we are going to consider the three discretized models, okay, of the first one is the accelerating power. Then we are going to consider the discretized model of this angular velocity, and then we are going to consider the discretized model for this rotor angle delta. Okay, and again here we are considering a constant time interval. Okay, that is the second point. Here the time interval is assumed to be constant, and that interval is nothing but this delta t. Okay, you see in this graph, this is the time interval. Okay, then we have this time interval. Actually this is half the time interval, this is complete time interval. Okay, this is from n minus 2 to n minus 1, this is the one time interval. Then from n minus 1 to n, this is the another time interval. So this time interval is kept as constant, or it is assumed to be constant in this discussion. Okay, so here we are going to take the help of the three uh, discretized model, as I have already told here. So these three discretized model, what we are going to do in this three discretized model, let us discuss that here. The first model we are considering here is a graph of accelerated power with respect to the time. Okay, the time here we are considering is a t by delta t. Okay, the second graph what we are going to consider here for the discussion of point by point method is change in angular velocity. Okay, so we can call it as change in speed, again with respect to the time interval, that is t by dt. And the third one is change in load angle or the change in rotor angle. change in rotor angle again with respect to the time interval t by dt. Okay, see, whenever there is an accelerated power will be there, definitely the speed will change, and when the speed is going to change, the rotor angle will change. Okay, so we are considering here that the accelerating power will be there. Okay, it will because whenever disturbance will be there, accelerated power will be there. Okay, and depending upon the value of the accelerated power, the there will be change in the speed, and correspondingly there will be the change in the rotor angle. Okay, so that uh, graph we are taking here. Okay, so again here, now you see the swing equation whatever we are having, it is nothing but this one. The swing equation is m into d square delta by dt square is equal to pa, that is the accelerating power. Okay, see, I can rewrite this as d square delta by dt square is equal to p by m. Okay, now let us integrate this swing equation on the both side. Integrate on both sides. So what we will get here is d delta by dt will be equal to, see here we have to integrate this one p by m with respect to time. Now here we have to apply the time integration limits as well. So let us suppose that we are integrating over one time interval. So the time interval will be 0 to, let's say, delta t. Okay, so if we solve this, you will get here as d delta by dt is equal to, this p by m is nothing but it is constant. Okay, so here we will get this one delta. Okay, all this as equation number 1. Okay, now here you see that the first graph whatever we are having, that is the graph of accelerated power versus this time. In this graph you can see here the two solutions are showing. The one is the discrete solution and another is the continuous solution. First we are let us concentrate on this discrete solution. Okay, so what we are doing here is we are assuming that the accelerating power is constant for any interval. Suppose if I am considering this n minus 1th interval, for this interval the accelerating power will be constant from the middle of the previous interval, okay, from this point till the middle of the present interval. Okay, so this is the assumption. Okay, so what we are considering here, since we are considering a discretized model, so as per that the accelerating power will remain constant for this interval, and that interval will be nothing but middle of the preceding interval and the middle of the present interval. So that is the first point. Okay, so here let us put this point here. Okay, so this we can write here as the accelerating power calculated at the beginning of any interval, at the beginning of any interval. See, the accelerating power whatever I'm going to calculate in the beginning of this interval, let's say at n plus 1 interval, I'll get this value. Okay, whatever value is calculated here is assumed to be constant for this length. Okay, so I can write here as the accelerated power calculated in the beginning of any interval is assumed to be constant from middle of preceding interval to middle of present interval. Okay, so this is related to the accelerated power graph with respect to the time. Now the second graph we are having, it is related to the change in speed with respect to the time. Okay, now here the change in speed is assumed to be constant, for the given interval. You can see in this graph here we are considering that the for this interval n minus 1th interval, the velocity or the change in speed is assumed to be constant here. Okay, so I can write here as, from the second graph we can conclude here as, the velocity, angular velocity, is assumed to be constant throughout any interval, throughout any interval. Okay, now you see here why we are assuming it to be constant throughout any interval. Okay, you see here, from this one, from this to this, we are considering the velocity to be remain constant. Okay, and what value it will have? Its value is whatever the value we are calculating at the middle of the interval. So whatever value we are going to calculate at this point, we are considering this whole interval will be having the same value. Okay, so here I can conclude this as, the v is assumed to be constant throughout any interval. Okay, and its value is calculated at the middle of interval. Okay, then the next graph we are having, it is of this rotor angle, or the change in rotor angle with respect to the time. Okay, now you see that, let us consider one in time interval. Okay, now let us assume one time interval. Now I am going to consider the time interval as n minus 1. Okay, so at the end of this time interval, okay, I want to know the accelerating power. Okay, so let us calculate that. At the end of n minus 1th interval, accelerating power, it will be Pa in n minus 1th interval. It is equal to, we know that accelerating power is nothing but mechanical power minus electrical power. So electrical power, I can write it as P max sine of this delta rotor angle at n minus 1th interval. Okay, now we know that before the occurrence of the fault, or before the introduction of the disturbance in the system, we know the value of the rotor angle. So with that, we can I can write here as, the value of this one rotor angle, it is already known. Okay, or I can say it is already known, or it is already calculated. Okay, so we have got the equation for the accelerating power at the end of this n minus 1th interval. Okay, let us get back to that graph. Okay, looking at this graph, let's say what the interval we are considering at the end of this n minus 1th interval. Okay, so here we have calculated the value of the accelerating power. Now, since throughout this length, the accelerating power is going to be same, so the velocity, or the change in velocity, will remain same for this instant. Okay, for this time period. Okay, so that I can write here as, the change in velocity from this interval will remain same. Okay, so we can write here as, the change in angular velocity, okay, caused by the accelerating power, okay, will be constant. Okay, now what will be the time interval here? It will be for this time interval, because the accelerating power is going to be constant for this time interval. Okay, so now let us get that time interval. Now you can see the time interval for that velocity will be this one. It will be from n minus 1 3 by 2 to n minus 1 1 by 2. Okay, so let us, the velocity corresponding to this interval is nothing but omega n minus 3 by 2, and the velocity corresponding to this is omega n minus 1 by 2. Okay, so let us write that change in velocity which is caused by this accelerating power in that interval n minus 1th interval. Okay, so now we can write here as it will be angular velocity, it will be omega n minus 1 by 2. See, this is indicating the time interval minus omega n minus 3 by 2. Okay, now what will be the value of this? See, recall the equation number 1. Okay, so here we have got that d delta by dt is equal to uh, p by m into dt, okay, or delta t. Okay, again you see that velocity is nothing but, this angular velocity is nothing but change of this rotor angle with respect to time. Okay, so this angular velocity is coming as change of rotor angle with respect to time. So if we look at the equation number 1, this is nothing but pm by delta t. Okay, so I can write here as this is nothing but pm into delta t. So I can write here this change in velocity as the change in velocity, we can write here as the change in time, that is the time interval delta t upon m into this is accelerating power. So accelerating power pa in n minus 1th interval. Okay, so call this as equation number 2. Okay, now again in this n minus 1th interval, what will be the change in the rotor angle? Now I'm interested to know the change in this delta angle in n minus 1th interval. Okay, now you see here, we will refer the graph again. So here in this n minus 1th interval, the change in speed or the change in rotor angle, it is this one, that is change in rotor angle delta of del of delta n minus 1. Okay, and it is calculated as, or we can calculate this as nothing but the difference of these two. See, this value we can obtain with this. Okay, so I can write here as in n minus 1th interval, it will be the change in rotor angle in n minus 1th interval is coming as rotor angle at this interval minus rotor angle at this interval. So again, the change in the rotor angle at the end of nth interval or in the nth interval, we can write that the change in this rotor angle in nth interval, it can be we can get this as change in rotor angle as this rotor angle at nth interval minus rotor angle in n minus 1th interval. Okay, let us see in this graph. See the rotor angle in this interval. Okay, that is nothing but at this point. Now this is nothing but rotor angle corresponding to this time interval. Now I wanted to know the change in rotor angle. So that change in rotor angle will be given by this del of delta n minus 1. So this is nothing but del n minus 1 minus del n minus 2. Okay, now if you want to get this value, that is the rotor angle corresponding to time interval n, that is nothing but del n. Now if suppose if you want to get the change in rotor angle in this interval, so that will be nothing but del of this delta n. So we can obtain this as nothing but difference of these two. Okay, so that is nothing but del n minus del of n minus 1. Okay, now here you see this change in angle from n minus 1th interval minus angle in n minus 2nd interval is nothing but it will be, see, in this period, in this time interval. Now if you see the speed in this n minus 1th interval, the speed is supposed to be constant for this length. Okay, see, for n minus 1th interval the speed is supposed to be constant, and that constant value of speed is nothing but omega n minus 3 by 2. Okay, so with that I can write the change as it will be nothing but omega that is the velocity in this interval multiply with the time. Okay, because you see, uh, velocity, that is the angular velocity, is nothing but the change in rotor angle with respect to the change in time. Okay, so with that I can write this as the change in rotor angle will be nothing but velocity into time interval. Okay, so that change in velocity will be nothing but velocity, the change in rotor angle will be nothing but velocity into time interval. Again, for this one, for this change, we can write it as velocity in n minus 1 by second interval into delta t. Okay, now let us call this as equation number 3 and this as equation number 4. Okay, now subtract equation number 4 and 3. Subtract equation 4 and 3. Okay, so let us subtract this. So this minus this, what we will get? So here we are getting delta n minus 1 minus that change in rotor angle at nth interval. Okay, it is equal to, now don't use this values, use this, let us use these values. Okay, so on that, on this side we will get, see here both side we are having, in both term we are having this delta t, okay, or del t. So let me take this as common here only. So in the bracket we will left speed in this, in at this interval minus this speed at this interval. Okay, now recall the equation number second. The difference of these two is nothing but this value. Okay, the difference of these two is nothing but this value. Okay, so I can get this as, okay, so I can write here as, this is nothing but, see actually it is nothing but this minus this is equal to this. So we are getting here this minus this. So I can write here it as minus of delta t by m into accelerating power in this interval. Okay, and this is nothing but equal to change in rotor angle in n minus 1th interval and change in rotor angle in nth interval. Okay, if we rearrange these terms, so we will get here this minus, I'm shifting on that side, so I will get here change in rotor angle in nth interval minus change in rotor angle in n minus 1th interval is equal to, so we will get here change in time or the time interval square divided by m into that PA, accelerating power in this in n minus 1th interval. Okay, so again you see that change in rotor angle at nth interval, we can obtain it by change in rotor angle in n minus 1th interval. Okay, I'm shifting this term on that side plus this one, that is the in time interval square divided by m into accelerating power in n minus 1th interval. Okay, so from this, let us call this as equation number 5. Okay, again let me put this in the square bracket. Okay, so this, from this equation number 5 we'll get this value, that is the change in rotor angle in nth interval. Now how it is helpful, now recall this equation number 4. Okay, this equation number 4 is change in rotor angle at nth interval is nothing but del n, that is the rotor angle in nth interval minus rotor angle in n minus 1th interval. Okay, so I'll rewrite that equation again. So that equation is change in rotor angle in nth interval, it was rotor angle in nth interval minus rotor angle in preceding interval n minus 1. Now you see, if I reshuffle this, if I rewrite this as rotor angle in nth interval, it will be nothing but, okay, I'll shift this side, this term on that side, so I'll get here a rotor angle in n minus 1th interval, and again here plus the change in rotor angle in nth interval. So this is very important, the relationship what we are getting here, this is very important relationship. Okay, So what is the understanding we can get from this relationship is that, see, already we are knowing this value. Okay, already I told you that from the previous condition we will have the a value of what is the rotor angle. Okay, and after solving this swing equation by using this step by step method, we are getting this value. Okay, so once you get this value, if you put this value in this equation, so you will get to know what will be the rotor angle at this interval. Okay, and corresponding to this rotor angle, from the graph you will get to know the time period. Okay, if suppose if that rotor angle, if it is equal to the critical value, then the corresponding time will be equal to the critical time period. Okay, again, if suppose if you have not arrived at that critical value of the rotor angle, then you can repeat this process again. Okay, see, with the help of that accelerating power at n minus 1th interval, we have obtained this value. Suppose if I, for next interval, if I consider the accelerating power for this interval, for nth interval, then it will give me the change in the rotor angle in n plus 1th interval, and from this I will get to know, or I will get the value of the rotor angle at this interval. Okay, correspondingly from the graph, if we can get the time. Okay, we can get the time in that n plus 1th interval, and accordingly we can decide. Okay, if this value is approaching to the critical value, then we can treat that time period as the critical time period. Okay, again you see here that we have used here a discretized model. Okay, as long as we need to carry out this solution, we can continue to solve this or to repeat this as long as we require to do this. Okay, and here generally the time period is taken as 0.5 second. Okay, so suppose if you want to have the better accuracy, then in that case you can reduce this time period. Okay, but generally this is preferred. If you want more accuracy, then you can reduce this. Okay, once getting with that discrete model, then whatever values we will get on that discrete model, if I join those values, corresponding values, then I will get the corresponding solutions. Okay, you can see here I have joined those values. See, this was the value, this was the value for the accelerating power, and this was the accelerating power value. Okay, but we have discretized it. But now at the end of this, after getting the complete solution, we can join these points to get the smooth continuous solution. Okay, same we can do for the speed, and same we can do for the this rotor angle. Okay, by this way we will get to know the rotor angle and corresponding time period. Okay, again one more important point related to this solution of the swing equation is that, suppose there are some events when the accelerating power will get discontinuity. Okay, what are those causes? First let me write it down. So here the first cause can be the occurrence of fault, then removal of fault, then we can say initiating of any switching event. So these three event, or these three will cause discontinuity of accelerating power. Okay, so what will happen if suppose if this uh, events occurs in the beginning of any interval. Okay, so because what we are doing, we need to have the accelerating power value in the beginning of an interval. Okay, because whatever value we are getting in the beginning of an interval, we are considering that value to remain constant. Suppose here whatever value we are getting here, we are considering this value will remain constant for this time period. Okay, for this time interval. Suppose if one of those event, if it comes at this point, then definitely there will be a discontinuity in the accelerating power. So in that case, how we can solve it, or how we can do this, how we can obtain the value of that accelerating power, we can consider, or we can take the average value of the accelerating power immediately before the clearing of that fault and immediately after clearing of the fault. Okay, So this way we can calculate the value of the PA in this instant. Suppose the fault has cleared in the beginning of nth interval. Suppose the fault we have already cleared in the beginning of nth interval. Okay, so in that case we need to calculate the value of accelerating power in that time, okay, in n minus 1th interval. So how we can calculate it as, we can calculate it as the average of the accelerating power, immediately before the clearing of the fault and immediately after it will be minus 1 plus. Okay, so this is nothing but the accelerating power in n minus 1th interval. See, we have to calculate it because there is a discontinuity in the accelerating power at this time. Okay, so it can be calculated as average of 1 by 2 will be giving the, we are taking here addition and we are dividing it with 2. It means we are taking the average here. So average of what values? This is nothing but the accelerating power immediately before the clearing of the fault, and this is immediately after the clearing of the fault. Okay, so with this way we can compute the value of the accelerating power in the beginning of an interval if there is a discontinuity. Okay, and rest of the thing we can solve as per the things we have discussed in this uh, step by step or point by point method. Okay, thank you very much.